G'day viewers. In this segment I'm going to talk about the different kinds of network service models. So our topic is really the kind of service which the network layer provides to the transport layer. Like all good layers, the network layer is going to provide some kind of service interface to the higher layer, the transport layer in this case. And so what we would like to talk about is just what kind of network service is going to be presented by the network layer and how that service is implemented at routers. We're just going to talk about these topics at a high level, and in future segments when we dive into IP, you'll see how one of these models is realized in detail. So it turns out that there are actually two quite different kinds of service models that the network provides to the transport layer, both of which have been talked about a lot and experimented with in practice. One kind of model is what's called the datagram model, datagrams or connectionless service. The analogy here is the post office. So datagrams are just like sending letters through the postal system. They're self-contained units. You send them, you write your letter, you seal it up, you hand it to the post office. They're all treated individually. The post office delivers them by looking at the address and sends them on their way. This is very much like IP. IP is based on a datagram service. And that's really the way you might have expected the internet to look because of that. But there is another model here too. This other model is called the virtual circuit model, or a connection-oriented model. And the analogy here is one of the telephone system. You need to make some kind of connection, just like dialing someone, before you can use the network. But once you've made this connection, you can then sort of send data down the pipe and it will arrive out the other side. So this is quite a different kind of model. Both of these models have their pros and cons, and I think it's useful for us to know about both of them before we dive into the details of IP too much. So I'll also say that both of these different models are implemented with a technique that's called store and forward packet switching. Well, that's a bit of a mouthful. It really doesn't mean anything too complicated. It essentially means that the way routers are going to work is that they will receive a complete packet unit and they will store that packet temporarily while they work out what to do with it and send it out on the right link so that it's going to arrive at the destination. They won't necessarily need to store it for very long. In fact, they might only need to store it if there's contention for that destination. Other people are trying to use the link at the same time. One thing that's important about this model, that's one reason why it's used widely for all data communications networks, is that it uses statistical multiplexing to share the link bandwidth over time. In the description I gave you of having packets come in on links and simply sending them out links, what we're doing is we're sharing the bandwidth of all of the output links at a fine grain over time by sending different packets, maybe coming from different hosts and going to different hosts over that link. And we're using a bit of buffering inside the router to queue things up if you can't get on right away. So this is statistical multiplexing at work. It's quite different than dividing that link according to fixed time periods or fixed frequency periods like radio stations using the link. And it gives us many of the advantages of networks in terms of using the capacity well. As an aside, I'm going to dive into the store and forward model a little more, just to give you a better sense of what can go on inside these routers. So here's a fairly general model for all switching elements, switches, routers, funny devices that have a lot of input and output connections inside the network. They're all going to look something like this. They have inputs here. I've drawn the inputs on one side, so these will be plugged into ports, twisted pair wires coming in maybe, and they'll have outputs on the other side. Really, the input and output might be combined in a port, but it's more convenient for me to draw this from left to right. Inside the box, it's just another box. You can't, tell what the functionality is inside until you have some description of what layer it's doing the processing at and so forth. Inside the box is usually a switching fabric. That's what's providing the connectivity between different input ports and output ports. And what I want to highlight here is there's also necessarily some buffering. That's these pink things here that's both the input and the output. Why is the buffering? Well, there's buffering because maybe at the very same moment a packet came from this first input up top and it was destined for this output up top, And also a packet came from another link and it was destined for this output, and yet another link and it was destined for this same output. All three of those inputs can't go to the one output at the same time. So if the packets enter the switch, they need to be stored somewhere, either on the input buffering side or the output buffering side. But we do need buffering. And that buffering is just for temporarily holding the packets to help with our multiplexing of the output link. That model I just gave you is a little detailed in some ways, and it will often suffice to think of a much simpler conceptual view of what's going on inside a router. So here's another picture of a router. I've really drawn here just one output port, and in the simplified model here, we imagine that there is output buffering for each output port. So there's just one unit of buffering, and that unit is provided at the output port. That buffer, that big long buffer, is then filled up with packets. You can see I'm drawing them in here. As the packets come in from the input side and they're waiting to go out that output link. Exactly how that buffer is managed depends on how the router or switch is implemented. There are all sorts of different possibilities. But a typical one is to use a policy that's called FIFO, first in, first out. That just means that whatever packet gets in the buffer first is going to go out the output link first, and the rest of them will just have to queue up behind it. If this buffer gets full, by the way, there's no space and another packet comes, that packet will be discarded, or there'll be some discard policy. A packet will be discarded. So you can see here an important implication of these switching elements with buffering, and that's that packets may be discarded under load. This is actually what we refer to as congestion, and we're going to study it in a lot of detail later on. Okay, so now you know about some of the internals of routers. I'm going to tell you about the two different models we talked about in a little more detail. So first of all, the datagram model. Here's a network, and packets are going to go through this network between different hosts. In the datagram model, each packet contains a destination address, so every packet contains a full destination address. That's what the router uses to be able to deliver the packets onwards. Now the path through the network to get from one host to another might be this path here, initially. The way that will work is all of the routers, here A, C, and E, as a packet comes in, router A will look at the destination address, and if it sees it's, well, let's say it's really H2, but let's just say it's F over in this direction. A will look up in its table, see what it is, F, and it will learn that the way to forward it is along this path to here, in this direction. The packet will then arrive at C, which will go through the same process. But now realize, because every packet is handled individually, and a different process is responsible for maintaining the routes, it's possible that the routes can change while someone's using the network. At a later time, A might change its mind, and packets might follow a different route through the network. Thus, the host at the other end might receive its packets fine, but there might be strange delays or misorderings because the packets could actually have gone along different routes some of the time. We can just look at that in a little more detail, just to sort of complete our thoughts about the datagram model. These pictures here show you the forwarding table that's used at each of those routers. So here, over here, maybe is C's table. Here's C's table, and you can see that it has a table where for every different destination, it has a next hop to output the packet to. That next hop is really going to correspond to which output line you should send it on to send it to there. I've shown you tables here for A, C, and E, and A's table actually changes over time. Let's just imagine that we're trying to send a packet from A to F. And when the packet arrived at A, what A would do is it would look up in its table, it would see that it was going towards F, and the next hop for that is C. So it would then send it over the network, it would arrive at C. C would similarly see the packet's trying to go to F, look it up, see that it's meant to send it to E, and so on. It would get through the network. At some later time, A's table might change. You can see here that for some reason, routes towards the destination E and F have changed. They're now forwarded onwards to the next hop of B rather than C. Why? Well, we don't know why, but that doesn't really matter. We don't have control over it. We don't know when it could happen, but it could happen. The datagram model will still be fine. These packets, when they arrive, we will look up a destination like F. If another packet came, this time we would send it to B. Node B will have to look at its table and work out what to do, and maybe now we're following that other path through the network. So this is datagrams. The most popular datagram model by far is IP, the Internet Protocol, example of a datagram model. IP is the network layer of the Internet. It's what you have to use to be on the Internet, so it's used everywhere. It almost defines the Internet. The addresses I've shown you here, just shaded, these are the 32-bit addresses in IPv4. They're on each and every packet. Often packets might be up to around 1.5 kilobytes long, so you can see the picture here shows the header, which is going to occupy some number of bytes, not that many. If you've got 1.5 kilobyte packet, the overhead's not too much. There are various fields there, and the bottom one that says payload or TCP segment, that's all of the data of the packet beyond the header. Don't worry about all of these details on the header here, all of these different fields. They're the fun bits of IP that we get to go into in all of the segments which are coming up. But for right now, I just want you to know that IP is the most famous example of a datagram model that's out there, and we're going to look at it in detail to understand how it works. Second model. The second model I talked about for providing a network service to the transport layer was the virtual circuit model. Virtual circuit model is unlike a datagram model. Datagram model letters, everything's packet is independent, self-contained, fully addressed. Not the case in a virtual circuit model. In a virtual circuit model, just like the telephone, we go through 3 phases. The first phase here is a connection establishment phase. You've got to set up some connection or circuit from the person who wants to send to the person who wants to receive the information. Setting up the connection really means finding a path through the network, choosing that path, and setting information about the circuit that we're about to use in all of the routers that are along that path, so they'll know what to do when they see packets from this virtual circuit. Once it's set up, then there's a data transfer phase. This is the useful bit in some sense, the bit we want. We send packets along this virtual circuit, and all of the routers along the path forward them on to their destination. And then finally, when we're done, particularly if we're nice, there is a circuit teardown phase in which everything's cleaned up. The state about this circuit is deleted from all of the routers along the path in the middle of the network so they can forget about it and move on to new circuits. So this model is called a virtual circuit because it's fairly similar conceptually to a telephone circuit, but unlike imagining a physical wire or a certain level of resources that are reserved for a telephone call, it's virtual in the sense that there's usually no bandwidth associated with this circuit. The bandwidth across the links is still shared with statistical multiplexing. So how much bandwidth you get from this circuit is just going to depend on how much traffic you send and all of the other traffic in the network that was competing for it. Well, let's look in a little more detail. Here's our picture of our network again. Now, unlike packets in a datagram model, packets in a virtual circuit model don't necessarily, they don't contain a full address. All they need is a short label which says what circuit they're on. Hi, I'm on circuit number 7, so that the router will then know what to do with it. Because during the connection establishment phase, it's worked out what circuit number 7 means and where it should go. So these labels don't have any kind of global meaning. They just have to be unique to the link, to the router, where they're going to arrive on a certain link, so the router will know what to do. But they don't have to have any other unique meaning. In this network, we might have 2 different circuits going at the same time. Now, both of these circuits might be going along some of the same links. So here's one and here's another. Both of these circuits could be used at the same time. Maybe if host 3 and host 1, maybe if they're both sending to host 2. Well, let's just, because we're going to want to be able to send multiple circuits on the one link, otherwise we haven't got much of a network. Okay, let's look at just a little more detail. We looked at the forwarding tables inside a datagram network. Let's look at the forwarding tables inside a virtual circuit network. And the reason to do this is for you to see how they're different than the forwarding tables inside a datagram network. So now all we really need is a table which tells us the incoming circuits and what to do with them. by convention, the table tells you the incoming circuit, it tells you what link they're coming from. So something arriving at A could be coming from either host 1 or host 3, and what circuit number they have on the link they're coming in. These both happen to be labeled circuit number 1 on their respective input links. And then the output table tells us what to do. So you can see that the circuit that comes from host 1 with identifier 1 is forwarded out the link going towards C, where it is known to C as circuit number 5. What that means is that we're going to change the label or the circuit number inside the packet as it goes through the network. This packet is going on the link from A to C. It's identified by 5. When it arrives at C, it comes from A with 5, that's right, and what happens? We look it up in the table. We're meant to send it on to E with a circuit identifier of 1. So we're going to change that 5 to a 1, send the packet out the link to E. When it gets to E, what happens? It's coming from C with a 1, it goes out to F with a 1, and so on. I'll just go back now and consider traffic from host 3 going to F and eventually on to host 2, let's say. The reason to do this is because this circuit traveled down some of the same links. So we've got to be able to separate these two different circuits on this link. This example will show us how we do that. Now, the traffic from host 3 comes in with circuit identifier 1 to A. A has different input lines for host 1 and host 3, so it knows which one is which. When it gets circuit identifier 1 in from host 3, its instructions in its table here, and this is just one example, you could construct many different tables, but its instructions here is to send this packet onwards to C with circuit identifier 2. So we'll change the 1 to a 2, send it on to C. At C, this comes in on link A with circuit identifier 2. Note that both of these circuits at C came in from on link A. So we really needed them to have different circuit identifiers so we'd be able to distinguish them. We have, one's known by 5 and the other's known by 2. So we couldn't have called them both 1 going out C from A's table, because that would have resulted in confusion at C. C wouldn't have been able to separate these two circuits, but they have different numbers, so it can. Now we send it onwards to E with a circuit number of 2. E, when it receives it from C with a circuit number of 2, sends it on to F with a circuit number of 2, and so forth. They still have different numbers, so we'll distinguish these circuits. Okay, so that's virtual circuits. Here's a cleaned up version, and hopefully I've got everything right there. You can check that I got all the numbers right and work through it yourself. Okay, we all hear about datagrams a lot because that's what IP is all about. But I'm also here to report to you that virtual circuits are alive and well. Some of you might have heard of a technology called MPLS, multi-protocol label switching. This is a virtual circuit-like technology which is widely used inside ISPs. The way it works is that ISPs set up circuits inside their backbone from different ingress points to different egress points. So across their network, they set up all of these circuits. By doing this, they can carefully control the path through the network and, separate traffic in different circuits and handle them differently. It allows them better control over their network. This means, by the way, that when the packet comes in to the network, then the ISP network, since it's now using circuit switching, is going to need to add this MPLS header to the packets. So you can see a packet, here's an IP packet, came in, and what happened inside the ISP network is we added this MPLS header. That header, what's the most important part in it? The label we talked about. The label is this circuit identifier, which is going to tell routers inside the ISP which way to go. So this packet will then follow all of the labels to follow the circuit. It will eventually get to the other side of the ISP, and when it does, all of this MPLS header and the PPP link layer header are going to be stripped off, and we'll then be left with the IP packet, and we can then send that onwards to internet-style routers that understand IP as datagrams. I'm not going to go into more detail about MPLS. You can look at it in your book. If you want to know more about how ISPs work in detail, it is worth finding out about, although it's a bit of an advanced topic for our course. And finally, we're able to, now that we've seen these two different alternative service models to draw a bit of a comparison between them. So just on a bunch of different issues, you find that datagrams and circuits behave a different way. This is actually a good way to check your understanding of datagrams and virtual circuits. So let's go through them. First issue, a setup phase. Well, for datagrams, a setup is not needed. You just make your datagram, pack it, throw it into the network whenever you like. On the other hand, for virtual circuits, a connection setup is required. Router state. What do routers need to remember? Well, with datagrams, they just need their table of how to get to different destinations. With virtual circuits, they actually need to remember more. For every different circuit or connection through the router, they need to remember what to do about it. So you might have a lot of different circuits ongoing at the same time. Addressing. Datagrams carry the full address, an IPv4 address, say, of 32 bits, whereas a packet might carry a short label, 20 bits or less, 20 bits for the case of MPLS. Routing. Routing essentially happens on, you have to do the work for every packet, so it's on a per packet basis for datagrams. The routing for virtual circuits is really done when it's set up, and after that we're just sending packets down the circuit, however it is. So there's a chance to amortize work here across a whole circuit full of packets. Failures, on the other hand, well, in datagrams, failures are actually easier to mask because we're not storing any information in the network about a circuit and how to handle it. With virtual circuits we are, so if the router that holds that state blows up, we're kind of stuck, we've lost something and we have to scramble to do a lot of work to repair it. So in theory, datagrams should be easier to mask failures in than the virtual circuits. Quality of service is the other way around. With datagrams, every packet is handled independently. So it's hard to add quality of service because quality of service is usually not something that applies to an individual packet. Usually it applies to a group of packets, like all of the packets in a video conference, for it to be useful, for example. With virtual circuits, it's easier to add because we do have this identifier for all of the packets in a circuit. We might have one circuit for the whole video conference, for example. Okay, so now you know about these two different models, datagrams and virtual circuits, and we're going to dive into the datagram model in lots more detail as we go through IP.